Okay. So now I'm going to start sharing my screen, and you will tell me if you will be able to see my screen. Okay, just a second. Okay, share my screen. Okay, can you see my screen now? Yeah, okay, thank you. So I will go to full screen. Okay, and I will leave just myself. Okay. So can you see my screen, right? Yeah. Okay.
It's showing the Zoom launch screen right now.
What does it show?
The tab that it says the Zoom meeting is launched. So if you're trying to show a PowerPoint, I don't see that.
Okay. Oh, I see. Yeah. So now let me go to. Okay. Can you see the website page? Yeah, okay, thank you. So first, let me introduce myself. And this is a website of our university, local university, University of Victoria, Department of Physics and Astronomy. And I belong here to research personnel. You can go there, and here, this is my picture. As you can see, this is my name. You can go and check my website, okay. So my name is Pavel Denisenkov, and most of my papers are published under the name Denisenkov with double S. Some of them are published with last name Denisenkov with one S. So therefore, if you'll be interested to just have a look at my papers, you should search for both Denisenkov with one S and Denisenkov with double S. So otherwise, you will be surprised that Denisenkov with one S published just a few papers, okay? Okay, this is the first thing. And I will be I'm your computation coordinator, CaNPAN, as you know. So I will first try to give you some introductory lectures, stellar evolution, then a few lectures that will explain you how to use CaNPAN computational tools. And after that, approximately at the end of November, if some of you, I hope, will still be interested in continuing this work, I will be meeting you individually, personally via Zoom link to discuss with you your possible mini research projects. And then until the end of this academic year, until say the end of May 2023, I will be available to consult your mini research projects individually using for communication email, the CaNPAN Mattermost channel, and we will be able to have also individual Zoom meetings. Okay. So now I'm going to start with the CaNPAN website. Okay, it's canpan.ca. Okay. Okay. By the way, when I show you, say, this screen, how many people do you see on the right?
No one, it's just a screen.
But you can see the CaNPAN web page, right?
Yep.
Okay, that's good, because I don't know, I see actually every one of you on the right, but you don't see this. This is good. Okay, so this is only for me. I just don't know. Okay, so this is CaNPAN web page with address canpan.ca. You probably already had a look at this page. So first, let me just point you to on the first page of CaNPAN website. Let me just first point you to this announcement. there will be soon, actually in a week, CaNPAN annual meeting. As you can see, if you click here, it will be in Vancouver at the Triumph facility. I'm telling you about this because it's already late to register for it, of course. But as far as I understand, this meeting will be a hybrid meeting, meaning that I hope, I don't know exactly, but the talks will be available online. So therefore, I just wanted to point you to this meeting, okay? So the next thing that I wanted to show you on the CaNPAN web page is the second announcement here, report on CaNPAN activities for the last academic year, 2021-2022. That was the first year, and I didn't have many students, okay, but you can read about the last year CaNPAN activities. If you click this is just a PDF file with quite a few links, so just you can have a look at this site and see what we were able to do with students last year, okay? So now let's go back to the CaNPAN website. Now let's go directly to this training program page because it's about you and myself, training program. So you can read here about the main goal of the CaNPAN. Actually, the main goal, as is written here, of CaNPAN is to provide, in the first place, Canadian nuclear physicists and stellar astrophysicists with computational platform and computational tools that will help us to collaborate on identifying key nuclear data needs in this new dynamic nuclear astrophysics regime. But not all of you are, of course, Canadian nuclear physicists. So therefore, now for graduate students and postdocs, not only from Canada, but from CaNPAN's IRENA collaboration, they can also, as you know, apply to attend CaNPAN online lectures and tutorials, and possibly be mentored by myself through a Computation Mini research project, as you already know. So therefore, you can read this entire pages later if you have not done this yet. But now I'm going to go directly here. There is a link in this document to CaNPAN computation tools. So I'm going to go directly to this page, which introduces for you CaNPAN computational tools. And I will make several announcements there, going step by step. So when you click here, you will find yourself at GitHub repository where I keep this CaNPAN projects. So this is a public repository, so which means that anyone can clone its content. And I will show you in a minute how to do this and what you, but this doesn't mean that this repository will allow you to use all NuGrid code capabilities. So you should consider this, this repository as it contains something like an envelope around NuGrid codes, right? So it helps you to use these codes. It helps you to use the NuGrid codes via some README files, tutorials, as well as via some input and shell script files. I will explain this for you later. So this just doesn't mean that if you clone this repository, you will be able to use NuGrid codes. No, that's not true. I'm showing you this repository right now because you will have to do a few first steps for us to work later. Let me walk you through these steps, okay? So the first important thing actually, which is in my plan, is that it's here on step 3. So first of all, what you should do, you should go to GitHub, github.com, I think, github.com website, and register with GitHub. Register with GitHub, okay? This is the first thing you have to do. So the registration there is free for teachers, students. So if you have not done this before, go to the github.com, here, github.com website, and register there for free, for example, as a student or teacher, okay? After you will have registered there, please send me either via my email or via CaNPAN Mattermost channel. Please send me your GitHub, your name accompanied with your GitHub ID after your registration. Please send this information to the CaNPAN computational coordinator, which means to me. So this is necessary to do for you to get an access to AstroHub web service, to the computational platform, where you will be able to run some NuGrid codes, right? Because until recently, until recently, access to some of AstroHub computational platform was free for everyone in the world. But recently we experienced some hacking attempts, right, by some bad guys. So therefore, we had to close free access to one of our AstroHub gates, and now it will be free for you. But for you to get access there, I need to provide our computational administrator your GitHub IDs, so that the system will recognize you when you will attempt to access it for the first time. So this is an important thing for you to do, okay? Now, these are basic instructions on how to get started using CaNPAN projects tools on AstroHub web servers. So I recommend that you use as a web browser Google Chrome. It doesn't mean that it won't work on with other browsers, but sometimes there were some problems with other browsers. So therefore, if it's not a problem for you, we recommend you to use Google Chrome Internet browser. Okay. So I've already said you about GitHub IDs. You will do this and send me as soon as possible. Before next Friday, okay, at least your GitHub IDs. Okay, and now next thing. Next thing I want to show you how you can clone this repository. Okay, so for this, this is actually a README file. So some basic instructions, as you can see when I click to the name of the parent directory CaNPAN projects. Okay, I'm here. Now, as usually, how you clone a GitHub repository, you go here to this green button code, you copy the path, you copy, okay, and I will show you, give you the example how to copy this using. Just a second. Using our unique student web server, so that you are sure that I'm not using my laptop where everything may work, but on your laptop it won't work. So therefore, I'll go to one of our University of Victoria students web server, which is here, UVic CVG, okay. Okay, so okay, this here. So I sign in. Okay. Okay. So I open a terminal window. Okay. So this is a terminal window, a Linux terminal window, or you can say a Mac terminal window, right? Yeah. So this is, as I said, University of Victoria server. So therefore, I'm going to show you how to clone CaNPAN project tools repository here. So you just execute command git clone and the copied path to the repository, okay, like this. And it's getting cloned here. Okay, it takes maybe 1 minute, okay. Okay, so it's cloned. So if I check, you see there is a new directory with name CaNPAN_projects. So this is a directory from the repository. Now if I, now if I go back here, I can see this CaNPAN projects repository in the local Python notebook. When I go there, you can see inside CaNPAN projects repository, you can see subdirectories which are called stellar astrophysics, NOVA, X-ray burst, rapid P process, and the README file that I already showed you, right? Okay. I encourage you to clone this repository on your local machine, on your laptop, so that you at least can have additional look on the slides that I will be showing you during my lectures, the introduction to stellar astrophysics and the introduction to nova evolution and nuclear synthesis. Okay, these slides are here. So if I go to the directory stellar astrophysics here, you can see SA stands for stellar astrophysics _ intro introduction. This is Python notebook that contains the slides that I'm going to show you in my introduction to stellar astrophysics for you. If I click here, okay, you can see this is just a bunch of slides that I will show you later. I will start this today, okay? And at least in this server as well as on my laptop, but you can install this on your laptop if you want to. There is here this button. What you have to install if you don't have it yet, it's called, this is Rise slideshow, okay? Otherwise you don't have, you will not see this button. It's a lot, when I click it, so I'm in the presentation mode, right, for this slide. So I can go through the slides. I will do this later. I'm just explaining to you why you probably want to clone the CaNPAN project repository to your laptop so that you can have a more detailed look later to the slides, okay? Okay, now I'm going to close this and I'm going to go back to README file. Okay, here in the CaNPAN projects repository. Okay, now let's continue following these basic instructions. You will be able to do computations of nuclear synthesis on our University of Victoria, on our UVic AstroHub gateway. So let me just click it and show you how our AstroHub gateway looks like. Okay, here. As you can see, so this is a website, and each of these colored squares is a gateway to one of our servers, okay, at the University of Victoria. First of all, you will be able to use this gateway, which is called TINA. So TINA, as you can see, stands for Training in Nuclear Astrophysics. Okay, and TINA is an ARENA project through collaboration of GINA, Joint Institute for Nuclear Astrophysics, CaNPAN, and NuGrid. So TINA will allow you to do post-processing nuclear synthesis computations using only one zone model. One zone model means that you can run nuclear synthesis computations, say, either for a fixed constant temperature and density, or for a temperature and density as functions of time, which is called trajectory. So trajectory means here you provide temperature and density as functions of time, and you run nuclear synthesis computations for the provided temperature and density, how they change with time, or just for a constant values. This is what we call one-zone computations. Unlike one-zone computations, multi-zone computations means that you can do nuclear synthesis post-processing computations for the entire stellar model, for an entire model of a star. For instance, all our stellar models are one-dimensional, of course, right? For instance, let's take the solar model, okay? We know what the central temperature in the sun, it's around 15 million Kelvin, but at the surface temperature is around 5,000 Kelvin, right? So therefore, this means that temperature in the sun changes from the center to the surface from 15 million to 5,000 at the surface. And we can construct a one-dimensional solar model, which will provide temperature and density, first of all, as a function of radius, starting from the center, radius equals 0, up to the surface where radius is equal to the present day solar radius. Okay, this is what we mean by multi-zone. Multi-zone means that you provide temperature and density in multiple zones of your stellar model, from the center to the surface, okay? And of course, this temperature and density radial distributions, they of course can change with time because stars evolve. The sun evolves slowly, but other stars on some specific evolutionary phases, they can evolve relatively quickly, for instance, during nova explosion or X-ray burst. And then you provide NuGrid multi-zone code with temperature and density as functions of radius and as a functions of mass. And also the code takes as input not only temperature and radius in the multiple zones, but also diffusion coefficient, which tells the code where there is mixing inside the star in which zones, in the core, convective zones, and where there is no mixing. So this is just a brief explanation of the difference for you between one zone nuclear synthesis computations and multi-zone computations, okay? So as I said, TINA, this gateway, this server, in order to access it, I will need your GitHub ID, so please send me. So TINA will allow you to do only one zone computations, and this is because of the NuGrid code development policy. I will explain about this policy in a couple of minutes. So now, in principle, you can also have access to this gateway, which is called public and outreach. Okay, therefore it's called public and outreach. But still, I will need to have your GitHub ID, yeah, so that you can access it. In this public and outreach gateway, you will be able to run MESA stellar evolution code. I will show you, not today, later, how to do this. And you will be able to do some analysis, make some plots, and analyze data produced with multi-zone new grid computations for a bunch of stellar evolution models. Okay, so this is the second gateway that you will be able to access, even if you are not a new grid member. Okay, for those of you who are already or will want to become a new grid member, for those of you for new grid members, they can use this server, this AstroHub gateway, which is called the new grid Wendy. Web exploration, Wendy stands for web exploration of new grid data interactive. As you can see, it's only for new grid members. So now I need to explain you if and how you can become a new grid member. So for this, I have to go to new grid website, which is newgridstars.org, newgridstars.org. Okay, new grid stars, not star, plural, stars.org. Okay, this is a website of our new grid collaboration. Okay, so new grid codes, they are not open source codes. Okay, so in order to be able to use new grid codes, you have to become a new grid member. Okay, as you can see by clicking members, there are quite a lot of new grid members already. If I click here members, okay, you will see that members include universities and the list of researchers from these universities. This is, you can see UK, this is Canada, USA, Italy, Germany, Australia, etc. Okay, so I'm not going to talk much about this, but in order to understand how you can become a new grid member, you should read the new grid manifesto, which is here, manifesto. Okay, this is a document which explains the goals of a new grid collaboration and if and how you can become a new grid member. So basically, for a student to join a new grid, your supervisor has to become a new grid member. This is important. So, right, and for a supervisor to become a new grid member, supervisor has actually, you can read the manifesto, but the idea is that supervisor has to start collaborating with other new grid members. So to discuss with them his or her research project, intended research project, etc. And then it's, yeah, a new grid PIs will decide, okay, if, yeah, usually decision is positive. So I'm not going to talk much about this. So just to make my point, so let me go here, right? Yeah, again, back to us, to our AstroHub gates. So when I say that if you are not a new grid member, for instance, you can run nuclear synthesis simulations only using this TINA gate. This means that in TINA gate, you will not be able, say, to compile new grid codes. Instead, you will be using already compiled executable new grid code for one-zone simulation. So therefore, you cannot change the code, right? You cannot change the code. While in new grid Wendy, AstroGate, you will be able to compile new grid code, but for this, you have to be a new grid member, right? Okay. So now that's it with my explanation of AstroHub gates, public and outreach, TINA and new grid Wendy gates. Okay. So that's almost it that I wanted to tell you before probably starting my first lecture, the introduction to stellar astrophysics. So therefore, I'm going to make a pause here and ask you if you have any questions so far. You can unmute yourself here and ask the question, please. Go ahead.
I have one.
Yeah.
So for the TINA codes, I understand that we can't change the codes, but can we look at the whole code to understand what's actually happening behind?
No. Excuse me. No, you cannot look at the code because you can use only executable file, right? But yeah, this is probably, I will explain this later, not right now, but given that you asked already. So this TINA server, okay, has a bunch of README files, tutorials, and Python notebooks, right? Yeah. So that allow you to execute this one zone nucleate code, right? You will also have access to the code input files, right? Yeah. So therefore you can change the execution of the code as you wish, right? So therefore you will have quite a lot of actually possibilities to do research work. For instance, now we have developed a tool for one-zone simulation. So therefore, it can be run with TINA. It can be run at TINA. We have developed a tool that allows you to do Monte Carlo simulations, right, related to a reaction rate uncertainty study, right? For instance, you have a list of nuclear reactions that you think are important for your case, right? Whatever case is yours, for instance, nova explosion or X-ray burst explosion or whatever, right? You have a list of nuclear reactions that you think are important for your case. And now you ask the question, so as a result of nuclear synthesis, you calculate abundances of chemical elements and isotopes. Okay, they're called predicted abundances. This is what you get theoretically. Then, of course, ideally you are going to compare the predicted theoretical abundances with some observational data, right? To see if you can reproduce observational data or not with your model. Let's say that your predicted abundances more or less well fit the observed abundances, right? But then as a nuclear physicist, you want to ask a question, which reactions of your list of selected reactions have the strongest impact on a given predicted elemental or isotopic abundance, right? For instance, silicon or calcium, for instance, right? To answer these questions, because there are a lot of reactions which can affect this predicted abundance, it's a good way to do Monte Carlo study. Monte Carlo study means that you vary each reaction rate, right? In your list, you vary it. For instance, even if you have no yet an idea how much you can vary it, right? From experiments, if you don't have idea, you still can say, I'm going to vary each reaction from my list by multiplying it by within a range, the default rate multiplied by 10 and divided by 10 within this range, okay? And in the Monte Carlo study, of course, you will vary this rate by randomly selecting a multiplication factor with this range. Not just multiplied by 10 and divide by 10, but select randomly multiplication factor, say it will be factor 2 or 3, multiply by 3 or divide by 3, okay? And you do this with all reactions from your list, right? For this, you need to run Monte Carlo simulations say 10,000 random variations, right? And then you will use a notebook, a Python notebook that I have prepared, right, to analyze data of Monte Carlo simulations, right, to do correlation analysis that will show you which variations of which reactions have the strongest impact on a given predicted abundance, right? Yeah. And I'm telling you right now this because this can be done in TINA. This can be done in TINA. For this, you can use just one zone simulation because when you run Monte Carlo simulations doing 10,000 runs, of course, you need this to be done relatively quickly, right? So therefore, it's a good idea to use one zone simulations because they are like very fast. But you need to do them 10,000 times. And I can tell you that for I-process nuclear synthesis, 10,000 simulations like this, they take about 24 hours, right? One day, yeah. Imagine if we wanted to run these Monte Carlo simulations for multi-zone model, and I did that in the past. This will take about a week on a supercomputer, right? Yeah. So therefore, you probably don't want to do this right now. This can be done by you, say, with my consultation as a research project later. But for this, you will need to be a NuGrid member, right? Or be my student. I can co-supervise you with your supervisor like this, okay? I answered your question, yeah?
Yes, thank you so much.
Other questions, guys, before I will start my introduction to the stellar evolution. Okay, I don't hear other questions. Let's assume that there are no other questions. So therefore, now I'm going to start the first lecture. And the first lecture will be the introduction to stellar evolution, right? Okay. This will include some slides about stellar models, equations that describe stellar evolution, and nuclear synthesis. I think I need to do this so that later we understand each other, okay? We understand each other when we will work together on some research projects, because you should understand what, for instance, helium shell flash is, or ingestion of protons that makes carbon-13 pockets, because otherwise we will talk on different languages. So right now I'm going to start my lecture on the introduction to stellar evolution. Okay. So for this, I go to my CaNPAN project directory. I go to stellar evolution subdirectory. So these are the slides that I'm going to show you and comment on them. And as I said, you can clone this repository and have more detailed look at the slides later. So Jupyter notebook, okay. Yeah, one more thing I think I should add, just a second. Just a second. What I was. Just a second. So you're going to use CaNPAN website, training program, CaNPAN computational tools, okay? Yeah, so the last point in this basic instructions, right, on CaNPAN projects says that for the introduction to Git commands and Python programming language, you can have a look at the first sections in this GitHub repository. So if you're not familiar with Python programming using Python notebooks or basic GitHub commands, so I recommend you to go to this GitHub repository. This is actually a University of Victoria computational physics course, second year course. And I recommend you to have a look at the first sections of this course, which describe some basic Python and GitHub commons. So I will be assuming that you are familiar with this. This is not my responsibility to teach you, of course, to Python, etc. Okay, so now I'm going to start my lecture, the introduction to stellar astrophysics. Okay. Excuse me. Okay. Yeah, first of all, introduction to stellar astrophysics. So there is funny things here. Actually, astar in Greek means a star. So therefore, stellar astrophysics is, we don't need actually put here astra. So therefore, there should be ideally introduction to stellar physics, because astra means star. So stellar star physics, okay? Okay, so now, the first slide shows a picture which is probably familiar to everyone. This is how our universe has been developing since the Big Bang, okay? The most important things for us here, because we are interested in stellar evolution, and stellar nucleosynthesis, the most important thing, therefore, for us in this picture are the following. First, when the first chemical elements were produced, were made, they were made, as you know, within the first few minutes after the Big Bang. This is when approximately 75% in mass of hydrogen and 25% in helium were made, not in stars, but in the early universe. So later, when plasma cooled down and the first stars formed, first stars took work on making heavier elements, right, from the primordial hydrogen and helium. And now here we're at present, and we have a lot of chemical elements and isotopes. And the main goal of our research is to explain the origin of chemical elements and isotopes in the entire universe, right? So therefore, I start with this slide. Okay. So this slide, next slide, second slide, shows what is our universe made of. It's probably also familiar slide for you, but just let me summarize this. As we know now, the most energy in the universe is actually dark energy, as you can see, more than 70%, this blue part, dark energy. Almost the rest of it is made of dark matter, okay? So almost 95% of our universe is made of, we don't know what, right? Yeah, dark energy and dark matter, unfortunately. And only about 5% of our universe are atoms, baryonic matter, only 5%. And if we speak about stars, right, that then only about 10% of these atoms, only about 1/10 of these atoms is in stars. So in other words, less than 0.5% of total content of the universe is in stars, right? Only less 0.5%, okay? The rest of atoms, of these atoms, 90% of these atoms, the rest of them exist in the form of intergalactic gas, as we know, as we believe, right? So therefore, but speaking of stars, although stars are made of only about 0.5% of the total content of the universe, of course, stars are important because of the following things. First of all, stars make the most of the glowing matter in the Milky Way, right? When you look at the sky with the naked eyes, you see only stars. Planets, of course, planets, but in stars, right? So stars make the most of the glowing matter of the Milky Way, as well as of other galaxies. When we cannot see other galaxies with the naked eyes, but this is Hubble picture, deep field picture, Hubble deep field picture, and you can see very distant galaxies. But the light produced by these galaxies predominantly comes from stars, which these galaxies are composed of, right? So light, stars produce most of the light, okay? Now, let's go back to the first minutes after the Big Bang. As I already said, showing the first slide, that during these first minutes, only hydrogen, this red curve, hydrogen, and helium, this greenish dash curve, were made. Additionally to hydrogen and helium, helium-4, small amounts, small mass fractions of deuterium, hydrogen-2, helium-3, tritium, and lithium-6 and lithium-7 were made. You can see also that some beryllium-7 was also made, but as nuclear physicists, you must know that beryllium-7 is unstable, right? Yeah. Beryllium-7 decays on a time scale of 52 years into lithium-7. So therefore, to summarize this Big Bang, the so-called Big Bang nuclear synthesis, the summary is presented in this table. Only these isotopes were made during the Big Bang nuclear synthesis, as I already said: hydrogen, deuterium, tritium, helium-4, lithium-6, and lithium-7. And the second column gives mass fractions of these isotopes produced in the Big Bang, while the last column gives mass fractions of the same isotopes in the sun. So we can compare hydrogen from the Big Bang, about 75%, as I already said. In the sun, it's around 71, 72%, while helium in the Big Bang was produced in the amount mass fraction about 25%, while in the sun it's 27%. Obviously, this is because in stars, starting from after the Big Bang to the present time in stars, some hydrogen, initial hydrogen, was transformed into helium. So this explains it, this difference, okay? Okay, so I've just said the mass fraction, these are mass fractions, and this text defines the mass fraction of the isotope. So this is actually, it's usually denoted by capital X sub I. I just specifies what isotope I mean. This is just the total mass of this isotope, M sub I, divided by the total mass of the entire mixture we have. So therefore it's called mass fraction. Of course, it's also equal to the ratio of the corresponding densities. A density of the isotope divided by the total density. And because the density of the isotope can be represented as the number fraction of the same isotope, the number of particles of this isotope in the mixture, multiplied by the mass of one particle, which is atomic mass of given isotope I times the atomic mass unit, right? So therefore, this is a valid equation. Okay, so now I'm going to zoom this in and go to the next slide. Okay, so this slide shows the periodic table of chemical elements, but not in a standard form, but it stands in the form related to stellar nucleosynthesis, right? So therefore it's called here all the chemical elements heavier than lithium was synthesized in stars, because yeah, we know that Big Bang produced elements, isotopes only up to lithium in the so-called stellar nucleosynthesis. Everything heavier than lithium, all elements and chemical elements, isotopes heavier than lithium, were produced in stars. in stars of different generations or populations, starting the earliest stars are usually called population 3 stars. By some reason, not first. They're called population 3, the oldest stars in the universe. Then we had population 2 stars, and the present day stars, including the sun, belong to the population 1. Population 1 is present day, population 3 are the earliest stars. And this periodic table of chemical elements, it shows, of course, the elements, but it also shows with color the source of this element, the source of this elements, which stellar or non-stellar source contributed to production of a given element, okay? First, you can see the blue color corresponds to the Big Bang fusion or Big Bang nucleosynthesis. And as we already know, we have just a few elements that were produced in the Big Bang. This is hydrogen, helium, not all of them, and some lithium, okay? Then the second color, I go to green color. Green color says its element was produced by exploding massive stars, okay? So when I say when the text says exploding massive stars, it doesn't mean necessarily that all elements colored with green were produced only during the explosion of massive stars. They were produced not only during the explosion, or maybe not during the explosion, but also during the entire evolution of massive stars. So this exploding massive stars means the hydrostatic evolution before the explosion and during the explosion, okay? And this is shown with green color. And yeah, so now next I go to yellow color, because unlike massive stars, yellow color shows stellar nucleosynthesis by low mass stars. It says dying low mass stars. Again, dying, like exploding, means not only during the death of low mass stars, but during also, including their entire evolution. Yeah, actually closer to the death, because we know that low mass stars, they begin to lose mass closer to their death. But this also includes the entire evolution, so yellow. And you can see, for instance, I take carbon and nitrogen. You can see here both green and yellow color, which means that both carbon and nitrogen we think, were produced by both massive stars, green color, and by low mass stars. Oxygen, as we think, was predominantly mostly produced by only massive stars, etc. Okay. Now, finally, interesting things happens when we go to heavy elements, say beyond iron peak elements. Here you can see we switch from the production of elements in during hydrostatic and explosive evolution of stars. We switched here to these colors, yellow and brown. Let me start with brown color. Brown color says this is a result of nucleosynthesis in merging neutron stars. And this text, merging neutron stars, actually refers to our process, to rapid process of neutron capture, okay? And of course, now we know that rapid our process, the rapid process of neutron capture by iron seed nuclei, which makes these elements heavier than iron, it probably most likely occurred and occurs not only in mergent neutron stars, but also in some supernovae, some specific supernovae. So therefore, when this color says mergent neutron stars, it doesn't mean per se that this is only mergent neutron stars. This is just refers to our process. And now, thanks to LIGO observation of mergent neutron stars, we do know that merging neutron stars do produce our process elements, okay? Okay, so along with our process elements here, brown color, as you can see, these elements share production with yellow color. And yellow color goes back to dying low mass stars. But this yellow color here, because these are heavy elements beyond iron, this is also neutron capture process because, yeah, I will show you this later, but probably most of you already know this. Elements heavier than iron cannot be made in fusion reactions, okay? They can be obtained only from iron seed nuclei in the process of neutron capture. And unlike red color, which corresponds to rapid process of neutron capture, yellow color refers to the so-called S process, or slow process of neutron captures. And we believe that the S process predominantly occurs in low mass stars. Again, not in, per se, dying low mass stars, but during their evolution in low mass stars, and we will talk about this later, okay? Okay, and that's almost it, except there are just two elements, maybe three, which are shown here with this pink color, excuse me. Excuse me. The only color which is left, I have not explained it, this pink color, okay, or not violet color, okay. And there are only two elements which are believed to be produced in this process, which is called cosmic ray fission. And this is beryllium and boron, okay. We know that beryllium and boron, we know they were not produced during the Big Bang, but there are substantial amounts of beryllium boron in the universe, and they cannot be produced in fusion reactions. So researchers believe that they were produced in the so-called cosmic ray fission or spallation reactions, when high energy cosmic protons, particles hit nitrogen and oxygen and split beryllium and boron nuclei as a result of this fission, okay? So now let's go to next slide. Okay, okay. So now the chemical composition of the human body, the chemical composition of our cells, right? Yeah. We know that we are predominantly made of water, protein, fat, carbohydrate, and minerals, right? Yeah. But these molecules are made of the following chemical elements: oxygen, 65% in our human bodies, carbon, 18%, hydrogen, 10% in water, mostly in water, yeah, etc. I'm not going to read all these names, but we know that all these relatively heavy elements, that they were not produced during the Big Bang. They were produced in stars. So therefore, our bodies are made of a material that sometime in the past was synthesized in stars. So therefore, as Carl Sagan said, we are actually stardust. We are star dust, okay? Our bodies are made of course, hydrogen comes from the Big Bang. Okay, great. Hydrogen comes from the Big Bang, but the rest of our of human body's chemical composition was made in stars. I think it's an interesting thing, but most of you probably know this. Let me just repeat. Not all things that I'm showing you on the slides, I'm sure not all of them are known for you. Some of them are known, but let's just go through the slides so that later I assume that we understand, we have used the same language, right? Okay. Okay, so next slide, chemical composition of the Earth's crust. Okay, the same thing as with human bodies. Earth's crust is made of relatively heavy elements, okay, oxygen, silicon, aluminum, iron, calcium, sodium, potassium, magnesium, etc., titanium, right? Those elements were also made, synthesized inside stars, okay? Okay, so now let's come back to our closest star, to the sun. Okay, sun itself constitutes almost 100% of the total mass of the solar system, 99.98%. Okay, so therefore the chemical composition of the sun is also called the chemical composition of the solar system. And it's important to spend some time talking about solar system chemical composition, because when you do nuclear synthesis computations, you have to start with some initial chemical composition, right? Yeah. This initial chemical composition in your computations can be weird, but it can, in most cases, in many cases, it's either solar chemical composition, because most, especially present-day stars, population 1 stars, most of them have solar chemical composition. Or if you go to earlier stars, population 2, population 3, they didn't have solar chemical composition, of course, but most of them had the so-called solar scaled chemical composition, which means they had much smaller amount, mass fraction of heavy elements of like iron, but the relative distribution of our elements was similar to the solar ones. They were all just lower than in the sun. This is what we call solar scaled chemical composition. We need to have some initial chemical composition for our nuclear synthesis computations, stellar nuclear synthesis computations, right? So therefore this slide. Solar chemical composition can be determined in two ways, either by analyzing the solar spectrum, and this is where stellar spectroscopy or solar spectroscopy methods are used, obviously, by analyzing spectrum, radiation spectrum of the sun. The second way, which can be used in the solar system, is to analyze chemical composition of meteorites, okay? Chemical composition of meteorites. And it turns out, and this left bottom plot shows, that chemical composition determined from the solar atmosphere, it's plotted along the vertical line, and chemical composition in the solar system determined by analyzing composition of, in this case, carbonaceous chondrites. These are meteorites. As you can see, it's actually the same. So, which means that these meteorites were made of the same chemical composition of which the sun was made, right? So therefore we can use as our as a source of data for the solar chemical composition, either solar atmosphere or meteorites, okay? Okay, so now this plot shows the distribution of abundances in the solar chemical composition. So as a function of atomic number, the vertical axis gives a decimal logarithm of the number of atoms. And it's scaled in such way that silicon has the value 10 to the 6, or decimal logarithm 6. You can see silicon and magnesium here. But so solar abundance is normalized to, this is type or 10 to the 6 silicon atoms. Of course, the most abundant hydrogen, as we already saw, helium, but this bright green band shows that more than 91% of the solar chemical composition is within chemical elements from carbon to iron, elements heavier than iron contribute a very small fraction to that solar chemical composition, as you can see from this slide, okay? Okay, so this table summarizes parameters, the basic parameters of different solar chemical composition. When we talk about solar chemical composition, there are different data for it. And this data here is taken from the from this paper, Asplund et al. This is Annual Review on Astronomy and Astrophysics, the year 2009. And this different solar chemical composition are called solar mixtures, because solar mixture. For instance, I can ask you a question: what solar mixture did you use in your nuclear synthesis computations, right? What solar mixture did you use? And you can say, I used Anders and Grives 1989. Nobody, actually nobody now uses this. This is the oldest mixture, so therefore I will not ask you about it. But starting from this 93, different researchers use these mixtures, including 93. This is Grives and Noels, it's known, GM93, Grives and Noels 93. You can see this mixture has, so Y, capital Y, is the mass fraction of helium-4, okay? Just capital X here, yeah, it's explained here. Usually capital X is the mass fraction of hydrogen, capital Y is the mass fraction of helium-4, the most abundant elements, and Z is the rest of mixture. So therefore, Z is equal 1 minus X minus Y. It's called the mass fraction of heavy elements, or elements heavier than helium. So therefore, the sum of X and Y and Z should be equal 1, okay? And Grives and Noels 93 give for the mass fraction of helium this value, 0.2697, for mass fraction of heavy elements, 0.011, etc., and so on. Grives and Sowal. So far, the most popular mixture that I use this mixture is Asplund et al. 2009. Surprisingly, as you can compare with our mixtures, it has relatively small mass fraction of heavy elements, 0.014, compared to Grives and Noels 93, 0.19, right? And respectively, it has a higher mass fraction of helium, okay? So this is the most popular among nuclear astrophysicists and stellar spectroscopists mixture. Therefore, I used here the bold font to emphasize this mixture. And finally, at the bottom, I give just a link to actually this year publication where they proposed a complete even a newer mixture, okay? You can have a look at it, but I still continue to use Asplund et al. 2009 mixture, okay? Okay, so now, how can we be sure? So in order to say, understand the origin of chemical elements and isotopes in the universe, right? We already know, let's just summarize, we already know that most of chemical elements and their isotopes were made in stars, right? Were made in stars, yeah, most of them. So therefore, in order to understand the origin of chemical composition of the universe, we need to know how stars evolve, right? Here, by the question, how do stars evolve? I mean, we need to know how temperature, density change in stars during their lifetime, right? How the stars explode if they are massive, okay? Because explosion is different from the standard quiescent evolution of the stars. During explosion, temperature can reach very high values and density can, yeah, at the beginning of explosion, density is very high as well. So we need to know two pieces of information. One about how stars evolve, right? Meaning how temperature and density, and also mixing inside the stars, because mixing inside the stars also changes chemical composition. We also need to know about mixing inside the stars. Okay, this is the first thing, and the second thing then we need to use this information as input data to do computations of stellar nuclear synthesis. Okay, so therefore there are two types of codes, computational codes, that we as nuclear astrophysicists need to use in our research. The first type of code will simulate stellar evolution, right? And in this NuGrid tools, in CaNPAN tools, we using, as many do in the world right now, the MESA stellar evolution code, right? And the second thing, the second type of code, this is post-processing nuclear synthesis code. We take from the first code information about the change of temperature, density, and diffusion mixing coefficient, and use this information as input in the post-processing nuclear synthesis code, right? Yeah. Okay. So now, when we talk about stellar evolution, we need to know if our stellar evolution code, for instance, MESA, gives us the right stellar evolution models. How can we be sure that our stellar evolution models, our understanding of stellar evolution is correct? Okay, so for this we use various methods. One of them is we compare the predicted stellar evolution, and when we look at the star, we see actually only its luminosity, how bright the star is, and we can estimate its surface temperature, which is called effective temperature, or in other words, its color. The colder the star, the redder it is. The hotter the star, the whiter it is. So therefore, the color can be used as substitute for the surface temperature. Okay. Unfortunately, we cannot observe the interior structure of the stars except using some special methods, which are called astroseismology methods, which in principle, I'm not going to touch upon these methods, but they, or helioseismology, that gives some information about the internal constitution of stars. But otherwise, we can see only the brightness of the star and its color. But we can predict how the luminosity of the star, how its brightness and its color change with time as it evolves. And then we can compare this with observational data. But what can we take from observations that represents the temporary evolution of the stars, right? When I take one star or the other star, they have different ages, they are at different evolutionary phases. And the stellar evolution code like MESA predicts how a star with a given, say, mass evolves with time, right? In order to make such a comparison between prediction of theoretical predictions of stellar evolution and observation data, and therefore this slide is the next, astronomers usually use the so-called color magnitude diagrams of open and globular clusters, okay? So color magnitude diagram is just a diagram on which we plot the brightness of the star on the vertical axis, this is absolute visual magnitude, and the color of the star. For instance, this is brightness, capital V, in a visual part of the spectrum, and B is the brightness in the blue part of the spectrum. So therefore, when we take the difference B minus V, this gives us idea about the color of the star, how much radiation comes out in the visual part of the spectrum compared to the blue. So this gives us idea about the color. And then we observe stars in open and globular clusters and produce this the so-called color magnitude diagrams, like this one, for instance, or this one. You see that stars in these diagrams, they are not randomly distributed. They form they clump into certain sequences. They're called sequences, okay? And the idea of using open and globular clusters, the idea, not individual stars in the sky, is that in a given, say, globular cluster, and this is a color magnitude diagram, sorry, here. What's happened? So this is a color magnitude diagram of the globular cluster M5. The idea is that all stars in a given globular cluster, we believe, were formed at the same time in the past, at the same time, from the same molecular cloud, giant molecular cloud. So all stars in the same cluster were formed at the same time in the past and with the same initial chemical composition, okay? So therefore, open and globular, similar is for open clusters. So therefore, open and globular clusters give us a bunch of stars with the same age and with the same initial chemical composition. If all of them have the same age and the same initial chemical composition, what parameter then determines the spread on the CMD, on the color magnitude diagram? Obviously, the only parameter that can still change is the initial mass, because they have the same age, the same initial chemical composition, but they were born at the same time in the past with the same initial chemical composition, but with different initial mass. Some of them were initially less massive, other of them were more massive. So therefore, this distribution of stars in the same globular cluster corresponds to stars of the same age, but with different initial masses. So therefore, this title here says that CMDs of open globular clusters, for instance, this CMD here for the globular cluster M5 represents its isochron. So isochron is just the line of the same age. So this is isochron is the line of the same age, okay? And by doing stellar evolution computations, say with a method stellar evolution code, we can produce a bunch of stellar models with the same age and with the same initial chemical composition, but for different initial masses, right? Which means that we can plot on the CMD of a given globular cluster here a theoretical isochron, right? That will look like a line like this, okay? And then by comparing the observed CMD with theoretical isochron, we can get a lot of information about a given globular cluster, for instance, about its chemical composition and about its age, of course, right? But what's most importantly, we can test our stellar evolution code, our understanding of stellar evolution, at least for relatively low mass stars, as in this case. So therefore, I spent some time explaining to you this diagram so that you are mostly nuclear physicists, but you get an idea from the point of view of stellar astrophysicists that why CMDs, color magnitude diagrams of clusters, are important in stellar astrophysics, because this is main comparison tool for our predictions of stellar evolution obtained with stellar evolution codes. So I'm going to stop explaining this slide here. And next slide just complements what I said about the previous slide. So here, this is the observed color magnitude diagram because it's called CMD, color magnitude, because we plot color versus magnitude, B minus V, color versus magnitude V. So what's its corresponding theoretical analog? Theoretical predictions give us, instead of color, they give us directly the surface temperature of the star, which we call effective temperature. For the sun, this is 5,500 Kelvin. And instead of stellar magnitude, they give us luminosity of the star, the total energy that star emits from its entire surface per 1 second. We call it luminosity. So therefore, this is called a theoretical Hertzsprung-Russell diagram, where we plot decimal logarithm of luminosity divided by the solar luminosity to compare it with the solar luminosity versus decimal logarithm of effective temperature. So this is an analog of color magnitude diagram, the observed color magnitude diagram. This is its theoretical analog. It's called theoretical Hertzsprung-Russell diagram. Note that usually effective temperature increases from right to left, okay? So this is decimal logarithm of temperature, effective temperature, surface temperature, 10,000, 100,000, this is 1,000. And this is decimal logarithm of luminosity with respect to the solar. 0 means the sun, and you can see here we have 1 solar mass, and this small circle shows the position of the sun. Okay, this small circle, 1 solar mass. 200 solar luminosities, 10 solar luminosities, 1 million solar luminosities, right? Okay. Luminosity can be directly transformed in the so-called bolometric stellar magnitude using this equation. Bolometric magnitude, it's called bolometric because it includes radiation in all frequencies. So it's just a replacement of luminosity. But in order to get, say, from bolometric magnitude, say, magnitude in a specific photometric band like V or U or B or V, we need to use the so-called bolometric corrections. I'm not going into the detail because we are not going to focus on this. I'm just mentioning this here. And of course, we can directly relate from theory effective temperature, luminosity, and radius because we know the Stefan-Boltzmann law. Luminosity of the star is just 4 pi the stellar radius squared, the total surface area of the star, times Stefan-Boltzmann constant sigma, effective temperature to the power 4. This is basic physics law. And from this relationship, we find the linear relationship between logarithm of effective temperature here, logarithm of luminosity, and radius. And in this diagram, the line of constant radius, the lines of constant radius, they go diagonally like this diagonally. So therefore, when we see something like close to diagonal, this one line and this one line, these are lines of approximately constant radius, not exactly. And this line is called the main sequence. This is where most stars belong to, including our sun. On the main sequence, stars burn hydrogen in their cores. And this is the longest nuclear evolutionary phase of all stars. If we pick randomly a star in the sky, it with high probability will belong to this main sequence line. It burns, which means it's burning hydrogen in their cores, including the sun. This line, almost diagonal line, you can see it's located on the left, which means the radius is much smaller than for the solar type stars, for main sequence stars. And this line corresponds to white dwarfs. And they're called dwarfs because they have small radii. Their radius comparable to the radius of the Earth. So much smaller than the stellar radii, okay? And when we do stellar evolution computations, we usually plot them on theoretical Hertzsprung-Russell diagram. Then we can use bolometric corrections to transform our computations from theoretical plot to color magnitude diagram like this, compare with observational data. Okay, the time is up. I'm going to stop here, okay? And next time I will finish this introduction to stellar evolution. In the meanwhile, you can do please the following two things. Let me remind you. First, register with GitHub. Those of you who have not done this yet, send me with your name, your GitHub ID, so that I will give it to our computational administrator, and then you will get access to at least TINA gateway. And the second thing, you can clone this CaNPAN project's repository on your laptop and have a look at these slides, okay? Next time I will continue with this slide definition of a star, okay? So now that's it. I'm going to stop sharing my screen first, okay? And now I'm going to ask you if there are any questions. Okay. So it will take some time. So this introduction to stellar evolution, I will finish it next Friday, and then I will start to explain you how to use TINA, first TINA, right? And then we'll go to multi-zone computational tools, which are some of them. I mean, the envelope to them is in the repository CaNPAN projects. So after the stellar evolution, the next lecture will be about nova evolution and nucleosynthesis. This is a specific type of stars which explode from time to time. Okay, and using novae as an example, I will show you how to run stellar evolution code MESA, followed by it's post-processing, multi-zone nucleosynthesis post-processing, okay? I will give you directly, introduction to stellar evolution, then nova evolution nucleosynthesis, with examples how to run MESA and multi-zone NuGrid, right? And then TINA one-zone projects. My estimate that we will finish, given that we meet once a week for 1.5 hours, we will finish this in the second half of November, right? Yeah. And I hope that my video recording was successful. I'm going to record all online meetings so that, and I will give you links to videos so that you can watch them for the second time, just you missed something, okay? That's it. If you don't have any questions, I think we can stop here, okay? Yeah, the last thing, please don't hesitate to ask me any questions in between our meetings via Mattermost channel or directly via email. So I will be ready to answer your questions almost any time. Okay, that's it. Thank you. Bye-bye. Bye-bye, everyone.
Thank you, Papa.
Thank you.
Thank you. Bye.